In this video, we'll be talking about the basics of the one-way analysis of variance, or ANOVA. Specifically, we'll be talking about when we use the ANOVA, what it does, and some of the basics, including things like what is our comparison distribution and how we find our cutoff scores on our F table. So we're going to use our 5 steps of hypothesis testing, just like always, and we'll see that several of these, though, will be done differently since this is a different type of test from the z-test and t-test that we did in earlier videos. And so our first question is always, when do we use our test? And so for the one-way analysis of variance, or ANOVA, we're going to use the test when the population variances and population means are unknown, and that's going to be similar to the t-test that we talked about. And we're also going to use the analysis of variance in the case not only when these population variances and means are unknown, but also when we have 3 or more groups. And so this is going to differ specifically from both of the t-tests, but especially that independent t-test. We're going to see that this is actually really similar to the situation in which we use the independent t-test, except we have additional groups. And so instead of having 2 groups, which we were limited to in the independent t-test, here we can have 3, 4, 5, 6, as many as we want, and counting as far as we might need to. And so this is particularly a useful test if we have perhaps a control group and 2 or more experimental groups. It's also possible that we might have an additional control group in some situations. There might be more than one control and more than one experimental group, for example. And so, for example, we could have a control group that gets a placebo, we could have a group that gets medication, and we can have a group that gets therapy. Or we can have a group that gets a placebo, one that gets medication, and one that gets therapy and medication, or something like that. So what does the one-way ANOVA actually do? And so this is, just as it sounds in its name, this is an analysis of variance. And so it tests the variation among the means of the 3+ groups. And so what's really going on here is that we're hypothesizing about our means, but we are analyzing our variances. And we're going to do this, we're going to accomplish this by estimating our variances in 2 different ways. But it is important to note that we will still assume that our population variances are all the same. We're just going to have another way of estimating it. And so it's worth asking, how different can our sample means be? And so in particular, this does depend on the population's variances, but we're going to start thinking about where this variance comes from and how variance works in these groups. And so particularly, if we're thinking about our distribution that our population came from, we can think about our normal curve. And remember that this could be narrow or wide based on how much the scores vary. And so particularly when we look at these 3 curves, in this column here, and the 3 curves in this column here, the population mean of these, so the center point, we can see this with the triangle at the center point of each of these 3 curves have the same population mean, and these 3 curves have the same population mean. But these little dots that are in each curve, what those are is that's a random sample. Those are just 4 points that we've taken out of this curve. And if we get those means, and so we can see that what's going on here is we have these lines that are kind of going down to the bottom here, these dotted lines. These are the means that are graphed now for each of these individual random samples. And so we have a random sample from this group with its mean there, from this top group with its mean close to that, and this third group, the middle one, with its mean there. And what we can see is that the sample means will differ, but for these narrow distributions, they are still pretty well grouped together, those sample means. For these distributions, these wider, broader distributions, we can see the same thing. We can see that the population means are all the same, and we have random samples out of each group. We have their means graphed below, And we can see that these broader distributions have a little more variability. These sample means over here are spread out more than the ones over here. And this is a general principle. These sample means from populations with more variations are going to vary more. And so continuing to think about our variability here, it's the case that because of this relationship, we can estimate the variance in each population from the variance of the means in our samples. And so we can take our means, and if our means are really close together, we can assume that we aren't going to have as much variance. We can estimate that variance based on how close together those means are, or how far apart those means are, in which case we might think that variance, we might have a larger estimate for that variance. And so this is exactly what we'll be doing in the one-way ANOVA. And so in our case, if the null hypothesis is true in the one-way ANOVA, what this means is that we are going to have this between groups estimate of our population variance. And what that would mean, and so this is the estimate of the variance between the groups. So how different one group is from another group. And if the null hypothesis is true, if there is no effect of our medicine or our therapy or whatever it is that we're testing, then this between groups estimate of population variance represents just chance variation. And essentially, chance variation is just the fact that people are going to generally have different scores. If I give everyone a particular test or survey, everyone's going to answer a little bit differently, and that's for a variety of reasons. If we think of a test that you might take, there might be some people who got more sleep the night before, some people who studied more than others, or studied in a different way than others, some people who have just a natural understanding maybe of this particular topic, or have taken previous classes before, have more interest in the topic. There's all of these different kinds of individual factors that represent this kind of chance variation. And if the null hypothesis is true, this essentially answers the question of, well, why are our group means different at all? Why aren't they exactly the same? And this is because there's going to be some amount of chance variation, but that's all it is. If the research hypothesis is true, however, we're going to see that our between groups estimate is still going to include some chance variation, but now it's going to represent both chance variation and the fact that our population means are different. And specifically, when we say that our population means are different, because of this kind of experimental design, because of this kind of hypothesis testing procedure, we are able to say that this is because of the experimental manipulation. This is because of the effect of the drug or the therapy or the study strategy or whatever else that it is that we are testing. And so in this case, as in this picture here, we can see that if our experimental manipulation works, essentially one of these population means is actually going to be different because this is a different population now. This is not going to be the same because of what we've done. And so what is our comparison distribution here? And so this is going to be the F distribution. This is the comparison distribution for the ANOVA. And the shape here is quite different than what we've seen. Even though the T distribution was not normally distributed, here we see that we actually have a positively skewed non-symmetrical shape, which is quite different. And specifically, this is going to be a distribution of ratios of variances. And so because we're going to wind up getting a ratio for our sample score, we always need our sample score to match our comparison distribution. And so we need to compare against ratios of variances, since that's what our sample will look like. And like the t-test, the shape of the F distribution, or like the t distribution rather, the shape of the F distribution changes slightly based on the number of samples and the number of scores in each sample. And so what we're going to do is we'll be using that information in order to calculate our degrees of freedom and figure out what the shape of our F distribution is. And so specifically when we look at our F distribution, because of this positively skewed shape, and because it's a ratio, that explains this positively skewed shape. It can't be lower than 0, so we can't have a lower number than 0 for our F value. And that's because variances are always going to be positive, but they also can be a very high number. And so it's never going to be lower than 0, but it can just kind of keep going and being up to a very, very high number. And so this explains the skew. We essentially have a floor effect here. And so how do we calculate our degrees of freedom? We're going to have two different kinds of degrees of freedom. We're going to calculate our DF between, which is going to be the number of groups minus 1. And we're going to calculate our DF within, which is going to be similar to the idea of the DF total from our independent t-test, where we're just going to add up the degrees of freedom for each of our groups. As many groups as we have, we're going to add up those degrees of freedom. And so finally here, the last of our basic concepts before we start our ANOVA, how do we use the F table? And so this is what the F table will look like. And we're going to see that we have denominator degrees of freedom, our significance level, and numerator degrees of freedom in these last columns, and keeping going here to the right. And so first we're going to select the correct row, and this is going to be based on our DF within, which will be our denominator degrees of freedom. And we'll see that as we get into the main test here. But this will be our denominator degrees of freedom. So we're going to use our DF within and our desired significance level. So if I have 12, if my DF within is going to be 12, I'm going to go to these 3 rows here because they correspond to 12, and then I can pick my significance level from there. So if I wanted a significance level of 0.01, I'm going to use this exact row. If I had 12 degrees of freedom for my DF within and I wanted 0.05 as my significance level, I'm going to use this row. And then I'm going to select my column based on my DF between. And again, we'll talk a little bit more about this as we get into the main test. And so for instance, if I have my denominator degrees of freedom is 12, my DF within, and I have a significance level of 0.05, and my numerator degrees of freedom is, or my DF between is 2, then I'm going to go 12, 0.05, and over to 2, and I'm going to have a cutoff score of 3.89.